Hello everyone, I am Arinjita and today I shall be explaining our paper Efficient Attribute-Based Proxy Re-Encryption with Constant Size Ciphertexts. So this is a joint work done with Dr. Sharmila Deva Selvi and Professor C. Pandu Rangan at IIT Madras, India. So here is the organization for today's talk. First I'll be talking about what is proxy re-encryption and then the need for attribute-based proxy re-encryption or ABPRE. Then I'll be talking about the classifications and properties of ABPRE followed by its syntax and security model. I'll be then explaining what is collusion resistance in key policy ABPRE, the related results in this area and our contribution. After that, I'll be giving a description of our scheme and end the talk with concluding remarks. So what is proxy encryption? Proxy encryption is a cryptographic primitive which enables transformation of ciphertexts under one public key towards another public key with the help of a third party called as proxy. So proxy re-encrypts a user Alice's ciphertext towards Bob so that Bob can decrypt it using his own secret key. So this primitive was introduced by Blaise, Blumer and Strauss in 1998, and what is important to note here is that the proxy should not learn any information about the underlying file. So the traditional proxy re-encryption primitive enables only point-to-point communication. Now, there are many scenarios which might require the re-encryption functionality without any knowledge of the intended recipients. So in such a scenario, attribute-based proxy re-encryption comes to the rescue, which was introduced by Liang et al. In 2009 to enhance flexibility of decryption delegation power. So ABPRE integrates PRE with attribute-based encryption in which user's identity is generalized to a set of descriptive attributes. So ABPRE enables the many-to-many communication model, and then a very important application of ABPRE is data sharing in untrusted cloud storage. So here is an example of ABPRE. Suppose Alice, who has the following attributes, wishes to delegate her decryption rights to users who satisfy this given access structure. So as you can see, Bob, who has the attributes of a cardiologist and working at General Hospital, satisfying this access policy, will now be able to decrypt the ciphertexts which are initially encrypted towards Alice but not Carol. So in the context of attribute-based encryption, ABPRE is classified into key policy ABPRE and ciphertext policy ABPRE. So in key policy ABPRE, the private keys and the re-encryption keys will capture the access structures that specify what type of ciphertext the keys can decrypt or re-encrypt, while the ciphertexts are labeled with attribute sets. In case of ciphertext policy ABPRE, the user's private keys and the re-encryption keys are associated with attributes, whereas the ciphertexts are embedded with access policy information. So as you can see, CP ABPRE is the dual of KP ABPRE. In this work, we will only be talking about KP ABPRE. So there are various necessary properties of proxy re-encryption which are needed in various applications. So we will be talking about two such properties today. The first is in the context of direction of delegation, it can be categorized into unidirectional and bidirectional schemes. In unidirectional schemes, the re-encryption key will enable re-encryption of ciphertexts from one access policy to the other, but not in the other direction. In bidirectional schemes, the re-encryption key enables the re-encryption in both directions. Now again, based on the number of encryptions allowed, KP-ABPRE schemes are categorized into single hop and multi-hop schemes. In the single hop setting, a ciphertext can be re-encrypted only once. However, in the multi-hop setting, a ciphertext can be re-encrypted polynomial number of times. So we will be talking about single hop unidirectional KP-ABPRE schemes in this paper. So here is the syntax of the unidirectional single hop KP-ABPRE schemes. So first you have a setup algorithm which is run by a certification authority CA, which takes as input the security parameter kappa and the universe description U, and it generates the public parameters. Now we have a key generation algorithm which takes as input the public parameters, the master secret key and an access structure mrow, and it will output a secret key corresponding to mrow. Now suppose you have a sender who wishes to encrypt a file M towards an attribute set W. It runs the encrypt algorithm to generate the original ciphertext or the first level encryption, that is C, which can be decrypted only by users such that the attribute set W satisfies the access structure corresponding to the secret key of the user. So Alice, who has a secret key corresponding to M row, will be able to decrypt it. Now, in terms of the re-encryption setting, which we call as the second level encryption, the algorithms are as follows. First, you have a re-key generation algorithm, which is run by the delegator Alice, who is going to take as input her own secret key, that is the secret key corresponding to the access structure. It is going to take two access structures. One is the delegator's access structure and the delegated access structure and the public parameters, and it will output a re-encryption key which will enable transformation from the access structure M row towards the structure M dash row dash. Now this re-encryption key will be given as input to the proxy, which will run the re-encryption algorithm by taking as input the first level ciphertext C and the public parameters, and it will generate the second level ciphertext D. Note that D can be decrypted only by users who have the secret key corresponding to M dash row dash. Alright, and then on successfully running the algorithm re-decrypt, it will recover the original message M. Now, what is the correctness of unidirectional single hop PRE? So it consists of the following 2 points. The consistency between encryption and decryption is as follows. That is, for all messages in the message space, the messages encrypted towards an attribute set W, which satisfies an access structure M row, should be decryptable by the secret keys corresponding to M row. Similarly, for the consistency between the re-encryption and re-decryption algorithm, all the re-encrypted ciphertext which has been re-encrypted towards access structure M row should be decryptable by the corresponding secret key of M row. Now, next I'll be talking about the ciphertext, the chosen ciphertext attack security for the key policy attribute based proxy re-encryption schemes. So we will be talking about the security in this selective setting. So this is the game based security game which is played between two entities, that is the challenger and the adversary, where the goal of the adversary is to break the scheme and the goal of the challenger will be to break an underlying hard problem with the solution of the adversary. So the game proceeds as follows. First, you have a challenger which is going to run the setup algorithm and generate the public parameters and send it to the adversary. Now the adversary is going to generate a target access structure and send to the challenger. Next, it enters the phase 1 or the training phase, where it can generate various key generation, re-key generation, decryption or re-encryption, re-decryption queries for the challenger, who is going to respond accordingly. After this, the adversary is going to enter the challenge phase, where it sends two messages M0 and M1 of its choice to the challenger. Now the challenger will pick a message of its choice and an access and an attribute set W star of which satisfies the target access structure and encrypt the particular message M psi using the attribute set W star and form the challenge ciphertext C star and send it to the adversary. Now the adversary enters the second training phase, that is phase 2. And where it can similarly query the key generation, re-key generation, decryption and re-decryption algorithm, and the challenger responds accordingly. There are various constraints which are placed on the adversary in this phase depending on the security level of the game. And finally, the adversary is going to give out its guess psi dash. So the adversary is said to win the game if it can correctly guess the message bit which was used to generate the first level ciphertext, and the scheme is said to be NPRE CCA secure if the advantage of the adversary is negligible. We have a similar security game for the second level ciphertext security against CCA attack. So the only difference between the previous game and this game is that in the challenge phase, the ciphertext form is a second level ciphertext towards attribute set W star, which satisfies the target access structure M star row star. Now consider the following scenario. So you have a delegator Alice who satisfies the access structure M row, and she is going to store her second level ciphertext in the cloud. So let me remind you, the second level ciphertext in the single hop setting cannot be re-encrypted any further. Now Alice has delegated her decryption rights to an access structure m-rho-, which is satisfied by Bob. So Bob is a delegate in this situation. Now usually the re-encryption keys are generated in such a way that it is a function of the secret key of the delegator access structure m-rho, the access structure m-rho, and the access structure of the delegatee m-rho-. Okay, so as you can see, the ciphertext D cannot be re-encrypted further. So the only way for Bob and a malicious proxy to have access to the original file encrypted as D is by acquiring the private keys of m-rho. Now let us consider another situation. So usually the re-encryption keys are enabled for a bounded fixed period. So suppose Alice with an attribute set W which satisfies m-rho disables the re-encryption right of the proxy from m-rho to m-rho-, which is satisfied by Bob. So in such a case, the only way for a malicious proxy and Bob to obtain the ciphertext of Alice stored in the crowd is by acquiring again the private keys of the access structure m-rho, which is satisfied by Alice. So such an attack is called as collusion attack, where a malicious proxy and delegatee Bob with attributes W- satisfying m-rho- can collude to recover the secret keys of the delegator Alice with attributes W satisfying m-rho. And as I've already said, the re-encryption key is a function of the secret key of the delegator, the delegator's access structure, and the delegatee's access structure. Alright, so it is a very natural question to ask that what if the proxy and a delegatee colludes? Will they be able to recover the secret key of the delegator? So it has so be seen that all the traditional proxy encryption schemes are actually vulnerable to such an attack. And such a disclosure actually causes total damage of Alice's privacy. It can cause unauthorized sharing of confidential files, financial loss, etc. So hence, collusion resistance is a very crucial property in KP-ABPRE schemes as it places minimal trust on the proxy. So here is the security model for collusion resistance. So it is again a game played between the challenger and adversary, where the challenger is going to run the setup algorithm, generate the public parameters, and send to the adversary. The adversary is now going to generate a target access structure and send to the challenger. The adversary next enters the query phase, where it can ask for the key generation and rekey generation of keys of its choice to the challenger, and the challenger responds accordingly. And finally, the adversary is going to output a secret key SK, and the adversary is supposed to win the game if the secret key SK output by it is a valid private key of the access structure m*rho*, and the scheme is collusion resistant if the adversary's advantage is negligible. So in the context of key policy ABPRE schemes, there were only 3 attempts made in the literature to obtain key policy ABPRE. So the first one was by Lee et al., who gave the first construction of a CPA secure KP-ABPRE scheme in the random oracle model. Their scheme is collusion resistant, and it is secure under the DBDH model. DBDH assumption. Next, the same scheme was extended in the RCCA setting by Lee et al. In the random oracle model. However, the scheme was not collusion resistant, and the scheme is again proved to be secure under the DBDH assumption. Next, we have another scheme by G et al., which claims to be CCA secure in the standard model. However, it is not collusion resistant. So the first 2 schemes have this weakness that the re-encryption keys are generated by the PKG, which makes the scheme very much infeasible. And the latest scheme by G et al. Does not adhere to the standard definition of KBPRE. And also in our work, we show that the 2 schemes by Lee et al. And G et al. Are vulnerable to RCCA and CCA attacks respectively. So our contribution in this work lies twofold. So first, we are going to demonstrate attacks on the security of 2 KP-ABPRE schemes in the literature, that is the scheme of G et al., which claims to be CCA secure. We show that the scheme is vulnerable to CCA attack, and also the scheme by Lee et al., which claims to be RCCA secure. We demonstrate an RCCA attack on the scheme. Therefore, we propose the first construction of a selective secure CCA secure KP-ABPRE scheme in the random oracle model. And our scheme is proven secure under the decisional bilinear Diffie-Hellman exponent assumption. And our design allows monotonic access structure with constant size ciphertexts, and our scheme is based on the KP-ABPRE framework of Rao et al. And BLS sort signatures. So our scheme enables constant size ciphertexts, which is highly beneficial in scenarios with low bandwidth requirements and also which has the constraint of limited computing power. So next I'll be giving a description of our scheme. So our collision resistant KP-ABPRE schemes consist of the following algorithms. So in the setup algorithm, an admissible bilinear pairing E is chosen, where G0 is the source group, G1 is the target group. Both are of prime order P. G and G1 are generators of the source group. It is going to next pick a random exponent alpha, set it as the master secret key, and it is going to compute the public value y. The message space is of the size L power m. The size of the universe space is n, and for all the attributes in the universe, it is going to pick a random group element hy from the source group G0. And here are the public parameters which are generated, and the hash function description I'll be explaining as and when I'm going to explain the scheme. Next, we have a key generation algorithm which takes as input a shared generation matrix M and rho, which is the access structure. The size of the matrix is L times K, and this is again run by the certification authority CA, which is going to first execute the share algorithm to generate the shares of the secret alpha. It is going to obtain L shares of the secret, and for every row I of the matrix M, it is going to pick a random element Ri from ZP star, and it is going to compute the three key components Ki, Ki dash and Ki double dash as shown, and finally it is going to output the secret key. So as you can see, rho I essentially is a mapping function which maps the rows of the matrix M to attributes. Next, we have the encryption algorithm. So our encryption algorithm is based on the hashed Elgamal scheme crypto system. So our scheme will take as input a message, an attribute set W and public parameters. So it will pick a random string sigma and compute the value of S, and then it computes the value C0, C1, C2, C3, and C4 is essentially a BLS signature on the values W, which is the attribute set of the intended recipient, C0, C1, C2 and C3, and it outputs the ciphertext, the first level ciphertext C. Next, we have the decryption algorithm. So this is the first level decryption algorithm which will be run by any users who has the secret key corresponding to M row, such that W satisfies M row. And first it is going to check the ciphertext validity using the BLS signature which we have generated for the component C4, and then it is going to execute the reconstruct algorithm to generate the reconstruction shares of the secret, compute the values E1, E2, and then it is going to recover the original message M as shown below. I have shown the correctness. Next, we have our rekey generation algorithm. So the rekey generation algorithm will take as input the two access structures M row and M dash row dash of the delegator and delegatee respectively. It is going to choose theta randomly and two strings delta and gamma, and for every row I of the delegator's access structure matrix M, it is going to compute the components rekey 1i, rekey 2i and rekey 3i as shown here. And then after that it is going to pick at random an attribute set W dash which satisfies the delegate's access structure M dash row dash, and again it is going to compute the value S dash, the components of the rekey 4, rekey 5, rekey 6, and rekey 7 here is a BLS signature on the components W dash and the other rekey components. So the intuition as to why our scheme is collision resistant is over here. As you can see, the components in rekey 4, that is delta and gamma, is blinded with a random salt, which can only be recovered by the secret keys of a user satisfying the access structure M dash row dash. And also, if you see the component rekey 1i, the secret key of the delegator, that is Ki, can be decrypted only using the value of theta. However, the value of theta is chosen solely by the delegator, and here therefore it is infeasible for any other user to recover the value of theta and therefore retrieve the secret key value of the delegator. And this is how the re-encryption key is generated. Next, we have the re-encryption algorithm. So the intuition as to why our ciphertexts are of constant size is we increase the size of the re-encryption key and the secret key by a value of w, where w is the size of the number of distinct attributes. So in the re-encryption algorithm, we'll again do a ciphertext validity check as per the decryption algorithm of first level ciphertext. Similarly, we'll be doing a re-encryption key validity check using the BLS signature we just generated. We'll be then executing the reconstruct algorithm of the linear secret sharing scheme to generate the reconstruct shares of the secret. We'll be computing the intermediate values RE1, RE2, and then set the re-encryption or the re-encryption values as given here to generate the second level ciphertext D. Next, we have our re-decryption algorithm. So the re-decryption algorithm will take as input the second level ciphertext D, the secret key corresponding to m-row, m-row dash, which is of a delegatee, and the public parameters. So first it is going to do a ciphertext validity check, then it is going to execute the reconstruct algorithm of the linear secret sharing scheme to generate the reconstruct shares of the secret and compute the intermediate values E1 dash, E2 dash, and generate the values of delta and sigma as shown here. And using the value of delta and sigma, it is going to recover the original message M. So this can only be done using the secret key of the corresponding access structure m-row dash of the delegatee. So our scheme is selective CCS secure in the random oracle model under the assumption of n decisional bilinear Diffie-Hellman exponentiation, that is NDBDH assumption for both the first level and the second level ciphertexts, and also as per the theorem by Livert and Vergnaud, if a unidirectional single hop KPAB-PID scheme is CCS secure for first level ciphertext, then the scheme is collusion resistant as well. So our scheme is also collusion resistant. So for the details of the proof, please refer to the archive report number 2019-1325. So just to conclude the talk, we have demonstrated CCA attack on the only existing KPAB-PID scheme due to G et al., which claims CCA security and collusion resistant property, and we have given the first construction of a unidirectional KPAB-PID scheme with constant size ciphertext. And the scheme is selective CCS secure under the NDBDJ assumption in the random oracle model. That's all. Thank you.